right, so I wanted to start today with a look overall at some things that I kind of glossed over or maybe didn't mention as explicitly in our discussions on Wednesday. So one of those things that we need to look at a little bit more closely what do I do with charges? So if I'm asked to draw a Lewis structure, and I'm asked to draw a Lewis structure that has a charge on it, like the sulfate ion here with the -2, what do I do with that information? Well, what we have to go back to is kind of a fundamental understanding of what the charge tells us. So charges tell us if we have extra electrons or if we have fewer electrons than what we would have expected. So if I look at SO4, sulfur has 6 valence electrons. Oxygen also has 6 valence electrons. So 6 plus 24 gives me a total of 30 valence electrons for SO4. And so if I was looking at SO4 as a molecule without that charge on it, I would need to draw something that had 30 electrons in it. Now, what does that -2 charge do? That -2 charge tells us, okay, hold on a second. Yeah, I know you're supposed to have 30, but there are actually 2 extra electrons in the structure to give it this overall charge of -2. So instead of drawing something with 30 electrons around it, we actually need something that has 32. And so 32 electrons becomes the target, the goal of our investigation here. And we draw based upon the idea that we are aiming toward 32 electrons. Similarly, if I have a positive charge, it would go the opposite direction. So if this was SO4 +2 instead of SO4 -2, the positive charge means that there are fewer electrons. Electrons have been taken away. So instead of 30 electrons, if there were a +2 charge on this, we would have only 28 electrons, 30 minus 2. And so we would draw our structure with those 28 electrons in mind instead of 30. And so the way that we interpret that structure in terms of formal charges and does the sulfur expand its octet and all that other stuff becomes a relative exercise based upon the number of electrons that are there. So that's one concept that we wanted to talk about because it was something that we saw in the I3 ion. It was something that we might see in a couple of these other examples in the assignment 7-3. And we want to be aware of those kinds of things so that we can draw the correct structure when possible. Here's another thing that we would encounter. We see this especially for nitrogen molecules. Sometimes we see it with phosphorus and arsenic as well. This is a phenomenon that predominantly occurs with group 15. Odd electrons. So nitrogen monoxide, commonly known as nitric oxide, has an odd number of valence electrons. I've got 5 from the nitrogen, 6 from the oxygen. 5 plus 6 is 11. If I were to draw using the process that we talked about on Wednesday, the structure for nitrogen monoxide would look something like this, where I've got nitrogen single bonded to oxygen, and if I fill out all of the octets, it looks like this. And I counted up, I've got 2, 4, 6, 8. 10, 12, 14 electrons in this structure. And automatically I would look at that and go, 14, that's not right. I'm only supposed to have 11. Based upon what I was telling you Wednesday, every 2 electrons over means 1 more bond. Well, I'm 3 electrons over. So I know I need to add 1 bond. That 1 bond will take my 3 electrons down to 1. What do I do about that 1 electron? Well, I can't take away 2, so I can't make another bond. I'm going to end up with an odd scenario. I'm going to end up with a scenario where I have to take away 1 electron from the structure. And it becomes a matter of which one do I take? So let's draw this out with the double bond. And if I fill out the octets, this structure now has 12 electrons in it. How do I know where to take that 1 electron away? And here's where our discussion of formal charges can be really useful to us. Now, we know from the diagram that they give us what the correct answer is, and we know that the formal charges work. But if I was not given this, I could look at the formal charges in this structure and say, okay, for the nitrogen, I've got 5 valence electrons, 2 bonds, and 4 dots. That's a -1 charge. For the oxygen, I have 6 valence electrons, 2 bonds, and 4 dots. That comes out 0. So where do I take away an electron? Well, if I take it away from oxygen, that's going to make this 6 minus 2 minus 3. That's going to turn this 0 into a +1. As we discussed on Wednesday, electronegative elements don't usually take on positive charges. Oxygen's more electronegative than nitrogen, so that creates a problem of its own. And by taking the electron away from oxygen, I've created a molecule that has multiple formal charges on it. And chances are best that we really want to minimize formal charge whenever possible. We want as many zeros there as we can. This didn't help anything. It actually made it worse. So if I remove the electron from the nitrogen, like so, what does that do? Well, now I only have 3 dots instead of 4. 5 minus 2 is 3. 3 minus 3 is 0. My structure now has the correct number of electrons, and the formal charge has got better as a result of me taking it off of the nitrogen. That must be the correct move. So like we talked about on Wednesday, formal charges do help us to differentiate what the best structure is if I'm kind of caught in a decision. So my decision was, do I take off of the nitrogen or do I take off the oxygen? Formal charge told us that taking it off of the nitrogen made more sense. The formal charges improved as a result of that. Like I said, we see this a lot when it comes to nitrogen kinds of compounds. Nitrogen monoxide does this, nitrogen dioxide does this. A lot of nitrogen compounds work this way because nitrogen can't break the octet rule. And if we pair it up, anytime we have a total valence number that is an odd number, we're going to have one of these scenarios pop up where we end up with an unpaired electron. And that unpaired electron has a name. We call it a radical. one important thing about compounds that have radicals, because they do not have a full complement, they do not have an octet, radicals tend to be really reactive. And so nitric oxide, along with nitrogen dioxide, these are two primary components of air pollution. And air pollution can create surface level ozone. And one of the reasons why it can do that is because that reactivity there starts to mess up the oxygen at the surface level. The last thing that we want to talk about out of this particular unit is a definitive relationship between length, strength, and something called bond order when it comes to molecules, when it comes to chemical compounds. This kind of piggybacks off of the last thing that we talked about in Module 6. So if you go back to last Friday, we talked about heats of formation. We also talked about determining heat of reaction from bond enthalpy. This gets into what bond enthalpy is, how we determine those strengths, those energies, and this actually allows us to establish some trends that exist within those bond energies. So we can actually do a little bit better predicting qualitatively as well as quantitatively, using that delta H equation that we used last week. Something I want you to consider. What we have here, we talked about ozone on Wednesday. We have resonance. We talked about the idea of delocalization, the idea that this double bond here is not fixed in this position or in this position, but rather it bounces back and forth from one side of the molecule to the other. And the greatest evidence that we have for this is in the bond itself. As bonds increase in level, so as we go from single bond to double bond to triple bond, those atoms that they are attaching become more drawn to each other. And if you think about it, that makes sense. If the thing that is holding these two atoms together is the attraction to those electrons in the bond, the more electrons I put in those bonds, the greater the attractions are going to be. Well, if my attraction increases, my atoms are going to get closer together. And so it naturally follows that if I look at a single bond and compare it to a double bond, the single bond is going to be longer. There's going to be a greater distance between the two nuclei in the single bond compared to the double bond. And if I continue the trend, there'd be a greater distance between the atoms in the double bond compared to a triple bond. And so despite that kind of logical sense, we see that ozone doesn't have a single bond and a double bond. It has two bonds that are exactly the same. The bond length here between the oxygen in the middle and the one on the right is the same as the bond length between the oxygen middle and the one on the left. The only way that that can happen is if those two electrons in that double bond are not fixed in their position. They have to be moving around. That's the only way that we could explain why those two bonds are equivalent to each other in length, equivalent to each other in energy. Not only are they equivalent to each other in energy, as I was just talking about, there is a difference in length between single bonds and double bonds and triple bonds. As we get more bonds in between, we see that our bond length is going to get shorter and shorter still. Now, we call the number of bonds in a given compound, we have a term for that. It's called bond order. Bond order is simply the number of bonds that exist between one atom and another in a covalent bond. So in this example, where we have hydrogen peroxide, this is a single bond. The bond order here is 1. Here in molecular oxygen, where we've got this double bond, the bond order is 2. Here in ozone, we can tell from the distance, wait a second, it's not a single bond, it's not a double bond, it's kind of in between. So what do we do about bond order in those cases? The bond order has to be somewhere in between as well. For resonance structures, we can estimate the bond order by dividing the number of bonds that are being distributed divided by the number of atoms that are sharing them. So in our resonance forms of ozone, we have 3 bonds that are being shared, the double bond and this single bond. And we have 2 atoms, the one on the left and the one on the right, that are distributing those electrons. So the bond order is 3/2 or 1.5. And so with that bond order of 1.5, we would expect that the bond length would be between 121 and 148. And at 128, it is in between them. Now, is it exactly in between them? No, that's not a fair expectation, because it's a little bit more complex than just simply taking the average. But it is in between. And so when we talk about resonance, we talk often about, does this have more single bond character or double bond character? And we see in this instance, because of the bond length, we seem to have more double bond character. The bond length is a lot closer to the 121 than it is to the 148. For bond energies, again, kind of going back to what we were talking about last Friday with bond enthalpies. Bond energy is the amount of energy it takes to break 1 mole of these bonds. The bond length and energy are both kind of determined the same way. So at the fixed distance, that bond length, what we see is that there is a certain amount of energy that is kind of the maximum energy that is possible for those 2 atoms. What's important for us to know, not so much this graphical part, but this overall idea down here. As bond energies increase, or let me rephrase, as bond order increases, so does bond energy. And so what we have here is a kind of an interesting application of what we would call the transitive property in mathematics. But we've got three ideas that are all related to each other. Now, the slides here both phrase them in terms of bond order, but we could also phrase them in terms of each other. When bond order went up, bond energy went up. When bond order went up, the length of the bond went down. Well, put those two terms next to each other. Bond order goes up, bond energy goes up. Bond order goes up, bond length goes down. Well, if these two terms are equivalent and these two terms are equivalent, these two terms are equivalent. So if my bond length goes down, my bond energy would go up accordingly. So now we have three different phrases that can equate the ideas of energy to distance, energy to bond order, order to distance. Probably the easiest way, the best way to look at this is with a table like this. Now, last Friday, we saw a table similar to this. Here's the table in full form. And we can see, look, here was oxygen. Oxygen as a single bond, 142 kilojoules per mole. Oxygen as a double bond, 494. Now, is that just unique to oxygen? No. Carbon to oxygen, 358 as a single, 799 as a double. Nitrogen to oxygen, 201 as a single, 607 as a double. What about other size considerations? Nitrogen, oxygen to nitrogen, fluorine, 201 versus 283. We think about our periodic trend. As we go across a row, the atoms get smaller. Well, if the atom is getting smaller, the bond is going to get smaller too, because it's not going to have as many electrons to go through. What does that mean in terms of the energy? It increased. If the bond order, or excuse me, if the bond length goes down, the energy goes up. If I compare nitrogen fluoride to nitrogen chloride bonds, same thing. Energy is increasing in that particular instance. So what we can say is that those three things are definitively related to each other. And so if I needed to calculate a delta H, I could draw all of the molecules, figure out what breaks and what is reformed, and do it the way that we did at the end of module 6. Conversely, however, if I just want to know kind of generally qualitatively what's going to require more energy, this kind of bond or this kind of bond, I can use those three relationships to predict it without even pulling this table out. So if I want to know what is going to require more energy, a single bond between carbons or a double bond between carbons, I know from the relationship that the double bond is going to be harder to break. And so we kind of have two different ideas going on. What we saw last week was definitively trying to calculate the heat of reaction using these. Here, we're just talking about general relationships. And that concludes for us this 7th module over Lewis structures and general bonding characteristics. Any questions before we move into talking about module 8 and starting to put some three-dimensional ideas to this? All right, so I want to begin chapter module 8 here, looking at a structure very similar to one that we started with today. We started with nitric oxide today, NO. Now let's look at nitrogen dioxide, NO2. Based on what we know from this structure, which of these questions can we answer? So I want us to think about that. Based on what we know about electronegativity, can we determine if these bonds are polar? Yeah. Remember, polarity of bonds is just a matter of electronegativity difference. Is there a difference in electronegativity between nitrogen and oxygen? Yes. Pauling scale says it's about 0.5. That would put it on kind of the weakly polar kind of part of the scale. So yes, we know that these bonds are polar. Can we answer some of these other questions though? Based on this drawing, can I determine what the bond angle is? Now we'll talk about bond angle in a minute here, but if I was trying to measure the distance in degrees from oxygen to oxygen through that nitrogen, would I be able to do so accurately? It'd be a little bit hard. Based on this drawing, I would look at this and say, oh, it's probably about 180 degrees, right? It's half of a circle. In reality, it's a lot less than that. It's actually about 112 degrees. How did I come up with that number? We'll find out. Is the molecule itself polar? We know it has polar bonds. Does that mean it's polar itself? Not necessarily. So herein is kind of the problem with Lewis structures. Lewis structures are great at having us take a molecular formula and sketch out how that molecule is put together. Does a great job of predicting connectivity, like what atoms are connected to what atoms, but it doesn't do some things that are kind of important. First of all, it doesn't do a good job of predicting three-dimensional shape. And part of that is because we're really limited to a two-dimensional flat piece of paper. So there are problems with that. Other thing that it doesn't do, it doesn't give us a whole lot of room to figure out how it came together. So thus far, all we've done is we say, okay, well, this connects to this, and this connects to that, and this one has 6 electrons around it, and this one has 4 electrons around it, and this one makes 3 bonds, and this one makes 2 bonds. We talked about kind of what it looks like. We haven't talked about how it comes together. How do the electrons actually interact with each other? What causes that bond to be made between one atom and the other? Lewis theory didn't give us that. So what becomes necessary for us then is we need to try to address some of these shortcomings. And there are a variety of theories that do so. We're going to focus on 2 of them. We're going to talk about the valence shell electron pair repulsion theory, better known as VSEPR theory, and that's how we'll refer to it pretty much from now on. One of the main reasons why is that it's hard to say valence shell electron pair repulsion theory multiple times. And it kind of gets redundant, and it's just a lot easier to say VSEPR. VSEPR theory is going to be the topic of the next 8 minutes of our conversation here. It's also going to be what we spend the majority of Monday talking about. Hybrid orbital theory we'll talk about on Wednesday. Hybrid orbital theory is the nuts and bolts. How do those atoms actually come together to make those chemical bonds? Molecular orbital theory takes that a step further, but it's kind of beyond the scope of this course, at least for right now. And so if you're interested, the last two sections of the chapter in the textbook cover this. And it is really kind of fascinating and interesting how we get to bond order, how we get to talking about why things conduct electricity and why things don't conduct electricity from a molecular standpoint. But it's not something that we're going to talk about here. It's really not relevant to the rest of the conversation that we're having. Before we can get to VSEPR, though, we got to knock out some key terms. First term, electron pair geometry, sometimes known as the electron domain geometry, or just simply the domain geometry. In an electron pair geometry, what we are looking at is we're looking at the center atom of our molecule, and we're looking at how many electron groups are around it. And electron groups are composed of two types, the bonding groups and the non-bonding groups. The bonding groups, they're exactly what it sounds like, atoms that center atom is bonded to. The non-bonding groups, those are the lone pairs, the electrons that are on an atom but don't actually, make bonds with anything. Electron pair geometry feeds into something called molecular shape. The difference between a domain geometry and a molecular shape is the molecular shape takes that domain geometry and it says, you know what? We can't really see electrons. We know they're there. We know they influence the shape of the molecule, but we can't see them. So let's focus on the geometry of what we can see. The bonds, the atoms. And so molecular shape takes that overall domain geometry and simplifies it to just what is in the molecule from an atomic standpoint. But molecular shape is not a standalone idea. You can't just determine the molecular shape by looking at the compound, by looking at the Lewis structure. You have to know the domain shape first. The last term of interest for us is something called the bond angle. Bond angles are defined by geometrically how far apart is one bond from another bond in terms of degrees. And so those bond angles will always go through the center atom from one exterior atom to another. And they're always defined in degrees. All right, last concept that we want to look at, steric number. The steric number of a molecule is the sum of all of the different electron groups that are around it. So remember how I said that we broke down the groups into bonding groups and non-bonding groups? To find the steric number, we add the total number of those groups together. So we have, for the number of atoms bonded to the central atom, these are our bonding groups. The number of lone pairs, this would be our non-bonding groups. One important note about those bonding groups, we have to remember it's the number of atoms that we are bonded to, not the number of bonds. So if we have a structure that has a double bond or a triple bond, that double bond or triple bond counts as one bonding group. Because that double bond or triple bond is to one atom in particular. Non-bonding groups, in the rare case where we deal with radicals, radicals would fit into a non-bonding group as well. Usually we end up just talking about lone pairs because that's the most common kind of non-bonding group. But if I were going back to my original example here, where I had nitrogen dioxide, the steric number for nitrogen dioxide would be 3. Because it would have 2 bonding groups, one to this oxygen, one to the other, and it would have a non-bonding group because of that radical. So a total of 3 groups in that nitrogen dioxide, if we were counting them up. Now, the reason we focus on steric number is because steric number helps us to predict the geometries, helps us to predict what direction that things are going to go. There are a total of 5 different domain geometries, starting at steric number 2 and going up to steric number 6. And so what we will do first thing on Monday after we do the proficiency is we'll start exploring those 5 different groups and all of the shapes that kind of come out of them. And that'll be our springboard to doing some practice with shapes and kind of predicting things like bond angles and those kinds of things. So this is where we will stop for today. And we'll pick up further on Monday after the proficiency. Make sure that you answer this question on your way out. And once you do, you're free to go. Have a great weekend.